Hey guys, so we're doing the alkene reaction review, and I'm going over the first four reactions you've learned. And just bear with me, I already filmed this whole thing. It was an hour long, and then the recording was not saving onto my computer. So I already have all my notes drawn out, whereas I would have wanted to actually draw them myself while talking to you guys. So if there's any questions you have about my process, because I don't have time to redo the entire video the same way that I did it the first time, please let me know, and then I would be happy to show you like my exact process. But for right now, I have my notes already drawn out, and I'm just mostly going to be talking through them. So hopefully it'll still be helpful, and I do have a lot of notes and like tips that I can give you, even just if I'm just reiterating what's already written down. So yeah, let's get started. The first thing that I wanted to go over is just simply like to clarify why I might be preferring to draw one carbocation versus the other in these reactions, especially in the examples I'm going over. So two of the reactions we're going over have carbocation intermediates, the other two have bridged halonium intermediates. But for the carbocation ones, I'm always going to form the carbocation that's going to be more stable in the case where two of them are possible. So both in terms of real chemistry in a lab, both will form, but this one will form faster, it'll be more stable, and thus we kind of think of this not even occurring in an answer choice. If she ever asked you which one is possible, which one's barely ever going to occur, this is the one that's always going to occur preferentially because it has a secondary carbocation position versus a primary one as it's shown over here. So because of that, this is more stable. It's more substituted with these two carbon atoms versus this one carbon atom over here. So it's going to be lower in energy, and it's going to be preferred for our carbocations. So that's just a little something before we get started on the reactions. Just that's my rationale for why you might see me picking one versus the other, one carbocation versus the other. So let's start with the first reaction, hydrohalogenation. This is one of the more simple ones, and I think it's the first one that you guys learn for that reason. And it basically consists of reacting an alkene with a strong acid, which in this case, it's going to be an acid with a halogen. So we're not going to use like H2SO4 as a strong acid. We're going to use chlorine, bromine, or iodine as our acid sources. So this reaction consists of adding this halogen, whichever one we're getting from the acid, to wherever the carbocation shift is. So as you can see, looking ahead in this reaction, we are going to have a carbocation shift, and in some cases you might not have one, some cases you might, and I'll talk about why it's important to consider it in the very beginning of the reaction, because sometimes you can forget about it, and then that's a really easy point to not miss. So it's always important to draw the carbocation when you see it and draw that shift when you see it. The intermediate, like I said, is going to be that carbocation, so we have to take into account those shifts. And it also has Markovnikov regioselectivity and doesn't have any stereoselectivity, because stereoselectivity refers to reactions where we're adding two molecules at once. So in this case, we're only adding 1 mole of either chlorine, bromine, or iodine. So that whole stereoselectivity is irrelevant for this reaction. And at the beginning of each of these reactions I'm going over, I have a little like screenshot of my reaction guide I made. So just a reminder for you guys, make your reaction guides. I use them to guide me through Orgo 1 and even Orgo 2. So very helpful. And then you can see over here, I've also written that when we add this halogen to the carbocation, when we attack that carbocation, it's going to attack on either the top or bottom face. And basically, when I say that, I'm referring to the top, meaning wedged face. So we're going to draw that substituent on a wedge after the attack. And if it's attacking from the bottom face, it's going to be on a dash. And that's basically what I meant by that. So let's go on to our example. We have this alkene over here, just random made up molecule, and we're going to attack it or we're actually going to react it with this HCl molecule. So what's going to happen is we're going to have this electron source, which is our pi bond, abstract the hydrogen from this HCl. Abstract basically means it's going to grab this hydrogen, and the hydrogen is now going to be pulled away from the molecule it started off on. And therefore, we're going to move this pi bond or this sigma bond of electrons back onto the chlorine, generating a chlorine anion and a carbocation on this secondary position after we place this blue H on this position. So we're at this intermediate right here. Now, this is what I was saying. You've made the carbocation. Immediately before you move on, I would just take a second, especially when you're doing your practice problems and you're getting more used to these reactions. Think about all the possible shifts that can occur. You can already cross out a ring expansion because there is no ring. This is an acyclic molecule. But what about a methyl shift? What about a hydride shift? In this case, a methyl shift wouldn't work because think about moving this methyl group over here. It wouldn't accomplish anything because that would just move this carbocation to another secondary position because this methyl group would no longer be here. So a methyl shift is effectively not useful in this case. But the hydride shift would be useful, which is what I've drawn over here. When we move this hydride over here, when we move this hydrogen, we're doing that 1,2 hydride shift, and we're moving this carbocation that used to be on this position, which is this position here, onto this green position over here. And now this carbocation is on the position with our methyl group. And actually, let me redraw this. This was drawn later in my mechanism, but because there's a carbocation, we're not going to draw this methyl group on wedged or dashed face. It's just going to be simply in plane. So we have this carbocation now on the tertiary position, which is preferred over secondary, and we're ready to react it with our nucleophile. So I've labeled this entire molecule with the carbocation as the electrophile because it's an electron deficient molecule. And we have this chlorine molecule with that extra pair of electrons all the way from this step when we added that extra pair onto here. And because of that electron-rich molecule, we're going to call this our nucleophile. And this nucleophile can attack from either the top face, as I've drawn over here, but it could easily attack from the bottom face, like so. So it just doesn't matter how you draw your arrows. Obviously, I'm just drawing the arrows this way for understanding's sake, but on an exam, it doesn't matter which direction you draw your arrows in terms of the attack. Just know that when you draw your final answer, you do have to consider that the chlorine can attack from the top or the bottom face. So the chlorine is going to attack from top or bottom, but let's first draw the non-stereochem shown intermediate with this chlorine attacking. So we have this chlorine attacking on this green carbon. So it's going to be shown over here. And it's on the same carbon bearing this methyl group. So we have a chiral center over here. But I also wanted to point out we have a chiral center where this bromine substituent was attached all the way from the beginning. So even though I didn't start off with the molecule being shown in a wedge or dash, we are going to have to consider that because this yellow carbon is a chiral center, it can be drawn either in the dash form or the wedged form. And so that's why we have 4 possible answers, because first of all, we have to consider that there's 2 possible ways to draw this molecule with this bromine on a dash and then on a wedge. And then the second thing we have to consider is that we have a second chiral center with this chlorine and this methyl. And the methyl can either be on a dash if the chlorine attacked from the top face, or it can be on a wedge if the chlorine attacked from the bottom face. And this can occur either for this enantiomer or this enantiomer, where this bromine is actually on a wedge, on a dash, I mean. So that's basically hydrohalogenation. And this is a pretty simple example, but it still has a lot of complicated steps where a lot of people could get tripped up. So you could forget to do the carbocation shift, which is why it's really important to always remember to do that in practice. So you never forget it on the exam. You could have forgotten that this molecule or this side of the molecule is also a chiral center. So you could have forgotten to draw that in wedge and dash. So just small minor things can affect your correct answer. But as long as you do more practice problems with this, you'll start seeing all the possible different things that can be added into these mechanisms, and it will get easier. The next reaction I wanted to go over is acid-catalyzed hydration. And this also involves our starting material, which is an alkene, except this time we're going to react it with either water or an alcohol and a strong acid like HCl or H2SO4. And I can talk about why we can use an alcohol like CH3, CH2OH instead of water, but I'll kind of go over that at the end. So in our molecule or in our example, we're going to use water and we're going to use the strong acid H2SO4. But remember, you could also see an ROH or you could see HCl and it's still the same reaction. So in this case, we're adding OH or an OR group to wherever the carbocation is shifting. And once again, that O group, whether it's OH or OR, can be added to the top or bottom face of that molecule. So just something to keep in mind. And our intermediate is a carbocation, so possible shifts can occur. And we're going to observe Markovnikov regioselectivity, which means that the OH group or the OR group is going to attack on the more substituted side of the alkene. So let's start with our mechanism. So we have this double bond and we have an acid. How was this acid formed though? We have specifically as an acid, we have a hydronium ion. So in this mechanism, we always have to include a little section over here where we draw this acid-base mechanism, because that's essentially how we're showing how the product, the H3O plus, which is the initial electrophile, is forming. So in a mechanistic question, if you didn't include this in the mechanism, you could potentially get a few points off. So always remember to draw this. And it's just a simple acid-base equation. You have a strong acid, you have water. This water molecule is going to take away a hydrogen. It's going to become a hydronium anion or ion, and then this HSO4 is going to become HSO3 minus. So that's our acid-base reaction. We form the hydronium, and the hydronium is going to act as our electrophile, our initial electrophile, and this pi bond is going to act as our initial nucleophile because it's an electron-rich source. It's going to abstract this hydrogen. It's going to put the lone pair back onto the oxygen, and we're going to form a neutral H2O molecule and a carbocation in the secondary position. Once again, we're going to observe a hydride shift, and we're going to go on to this molecule where we have this tertiary carbocation now, and we're ready to react it with our second electrophile. Or we're ready to react it with our nucleophile, our main nucleophile, which is water, and this alkene or this carbocation structure becomes our second electrophile. So then we just do a simple attack of this electron-rich oxygen with the lone pair onto this carbocation. We end up with this molecule over here, which is our intermediate structure. And as you can see over here, it basically looks like our answer, which is just this OH hydroxyl group, but we need to deprotonate this extra H because oxygen doesn't like to have 3 bonds. And as you can see, it has a bond here, it has a bond here, it has a bond here. So we have water in solution. Water will always exist in solution. You can just assume that it's just going to be in excess. So water is a great deprotonating agent because it's a nucleophile, and it can easily grab one of these hydrogens, abstract it, and then put this pi bond or put the sigma bond electrons back onto this O group and make it a neutral OH substituent. And because I said that you can attach that OH group on the top or bottom face, I have one product drawn where the OH is on the top and one product drawn where the OH is on the bottom. And depending on which face I put the OH on, the methyl group went to the opposite face accordingly. So now going back to how I said you can use an alkoxy group, which is essentially an alkyl group, which is represented by R attached to an O group. The reason for that is because we just simply need to have an oxygen molecule with a lone pair that can participate in this acid-base reaction. And because an alcohol is equally capable of doing that to water, we can use alcohol in the place of H2O to form an ether structure, which would look something like this if we had used the CH3CH2OH group in the place of water for this reaction. It would have given us an ether structure with this O attached to 2 different alkyl groups on each side. The next reaction I'll go over is the addition of bromine and chlorine to our alkenes. So once again, alkene starting material, but now we have this X2, which X can be either bromine or it can be chlorine. And we're going to add 2 moles of that onto our alkene using an inert solvent. So I always recommend that even though this is an inert solvent, it's not doing anything in the reaction, always write it down in the reaction in case she's giving points for it, because it shows that you know all the reagents for the reaction. So it's always better to be safe than sorry and write down all the reagents for this reaction. So now that we're adding 2 molecules of something, in all the other examples we've done, we've just been adding 1 molecule, but now that we're adding 2, we're gonna have to take into account the stereo selectivity. And that's referring to whether or not we're adding these molecules on the same face or on opposite faces. And as you can see, looking ahead, we're adding them on opposite faces, which is why we call it an anti-addition. There's not going to be any notable regiochemistry because both sides of the alkene will have that halogen attached in the end, so it doesn't really matter which side you attack in the beginning. But you do want to keep in mind that the end product should have the 2 moles of the halogen added on opposite faces. As you can see here, that's what's been achieved. So going into our example, I wanted to point out that we're starting with a Z alkene, and that's going to be important because our structure, if we proceed with the Z alkene structure, will look different than if it was an E alkene. So we're starting with a Z alkene, we're going to form our bromonium bridge. And that's basically when the pi bond, our electron source, attacks this bromine. It bounces off this sigma bond of electrons onto the bromine, and now these 2 bromines are separated. And then the bromine can attack this pi bond right back. So it's kind of like a double attack. It's called a concerted mechanism, in case you were wondering. And that helps us form our bromonium bridge, which is right here. So in this step, I always recommend you guys draw your stereochemistry in your intermediate structure. So while this is an intermediate, it's not the final product, go ahead and draw your stereochemistry in this step, because if you forget to draw your stereochemistry in this step, it might make it harder to figure out what it's going to look like in the final product. So in this case, the stereochemistry is going to refer to which face the bromine bridge will form on. And it can either form on the top face or the bottom face because, like I said, these molecules are in free space and they can be oriented in relation to this alkene in any way. So I have drawn two examples. In this example, the bromine is on the top face, the wedged face. And in this molecule, it's on the dashed face. And the only important thing to remember between the two is that when you have it on the top face, then the methyl substituent that exists on this carbon will automatically go onto the opposite face. And that's just something to remember anywhere moving forward. When you have one thing on one face, the other thing attached to that carbon will always be on the other face, the opposite face, you can say. So that's what I've drawn here. We have the enantiomers. Both of them are electrophiles, which is how I've denoted them with this E+. And they are now going to be attacked by our second mole of bromine. And that's because this bromine is now a nucleophile. It has that extra pair of electrons from this step when it was like taken off of this Br2 molecule. And because of that, it has an electron source to attack this bromonium bridge, which is positively charged with. So this bromonium ion is going, or this bromine ion is going to attach on this side. It could attack on this side as well. As you can see in the product, it doesn't really matter which side you attack on. But for simplicity purposes, because there's less substituents on this molecule or this side of the molecule, let's attack on this side. So when we attack on that side, what we're doing is we're pushing off the part of the bridge that was anchored to this molecule. And we can highlight that molecule maybe in this color. We're pushing off that bromine bridge portion, and we're putting this bromine on the opposite face that the bridge was on. So once again, going back to what we said, if this bridge is on a wedge, then anything that we add to that is going to have to add on the opposite face. So we went from this molecule to this molecule, where we had this bromine on a wedge. We attacked this bromine on the opposite face and ended up putting it on a dash. And then this bromine is from the bridge species where it remains on a wedge with this methyl group on a dash. And then the same thing happened with this molecule, which is just the enantiomer of this. And that's how we got our bromine to be on a wedge this time, because we attacked a dashed bromonium bridge. The bromine will attack on a wedge, and then the other one will follow suit accordingly. So these are our two products. But one thing I wanted to mention is that these products can look vastly different depending on the orientation of these molecules. So as you can see here, we started with our Z configuration. We have a very visibly kinked structure where it kind of looks like that rather than our conventional zigzag. So because of that, this molecule looks different than this molecule, even though they're actually the exact same. So what is happening here is that we have an anti-addition. We can see clearly that they're on different faces. One's on a dash, one's on a wedge. But we can always rotate around this bond. And that's what I've done to this molecule. I've rotated around this bond, and I've turned it into its conventional zigzag conformation where it goes up, down, up, down, up, down. And when I did that, now this side of the molecule that I'm circling over there has the bromine on the same face as this. When you see something like this on an exam, you might think that it's no longer an anti-addition. You might think you did the problem wrong, but the fact is you did it right, because as long as you did the whole mechanism with this orientation, the kinked orientation you're supposed to start with, you'll see that it was indeed an anti-addition. And the only way to get from this anti-addition to this syn addition looking product is simply by rotation of a bond, which we all know occurs in free space for acyclic, non-hindered molecules. So that's just something to consider, something that a lot of people can get tripped up on. If you are asked to draw this product on a template that looks zigzag, even though you worked it out on a template that was kinked, all you have to do is rotate around a bond to get to that. And definitely don't freak out if you see these on the same face, because usually it only exists like that because you have rotated around the bond of the original molecule. Finally, we have addition of halohydrins, or HOX, and HO refers to basically an oxygen-containing molecule like either water or an ROH group, which is an alkoxy group, like I mentioned before. And then we're also going to add a halogen. So 1 mole of a halogen and 1 mole of an oxygen-containing compound. So the anti-addition of this will occur where one of them will be on a dash, one of them will be on a wedge. They won't ever be on the same face, and that's something to keep in mind. And then the intermediate is once again the bridged halonium ion. And in case I didn't mention this before, halonium just refers to the halogen. So in this case, it's a bromonium bridge because it's a bromine molecule. Once again, anti-addition, like I said, and there will not be any specific regiochemistry for the X or the halogen, but we will have Markovnikov chemistry for the O containing molecule, the oxygen containing molecule. We're going to put that OH group or that OR group on the more substituted carbon when we attack the bridged halonium intermediate. So let's get into the mechanism. We have this alkene that we're starting off with, and we're going to form that bridge. That's the first step. And the bridge is once again formed by attacking this bromine with our pi bond electron source. Then this bromine is going to pop off, and then this bromine is going to re-attack the pi bond and form this bridge, either on the top face, as I've drawn here on a wedge, or on the bottom face, as I've drawn over here on a dash. So now that we have this intermediate and it's positively charged, we can attack it with our nucleophile, which, as you can see, H2O will be our nucleophile in this example, but we could also easily have a nucleophile like this, CH3CH2OH, which is just an example of an alcohol. So that's just something to note. In this case, though, it'll be water, and we're going to have this OH2 group attack on the more substituted side of this bridged species. And that is referring to the Markovnikov regiochemistry. So this highlighted yellow carbon is going to be the more substituted carbon because it contains a methyl group and it contains this bridged species. Same with this methyl group and this bridged species. You can contrast that with this side of the molecule, which obviously is only attached to the other half of this molecule, whereas this half is attached to both the cyclic structure and the methyl and the bromine. So after the OH2 group or the H2O group attacks the more substituted side, what's happening here is that this bromine bridge part is going to break off, and this H2O is going to attack on the opposite face that the bromine was on. So let's just look at this molecule. Let's go step by step. So let's look at this molecule over here. The bromine is on a wedge on the bridged intermediate, which means that when this H2O molecule nucleophile attacks, it's going to have to attack from this dashed perspective. Then when this part of the bridge breaks off, it's going to leave this bromine group also still on a wedge. But what's going to happen to the methyl group that was attached to this yellow highlighted carbon? So I'm referring to this methyl group over here. The methyl group is actually going to switch spots with whichever face the bromine bridge was on in this carbon. So this methyl group will now be on a wedge because this OH group is forced to be on a dash when it attacks this bridge species. So that's just something to remember whenever you have this OH or whatever oxygen-containing molecule attack the more substituted side. The other substituent, like this methyl group, will switch spots with whichever face the bridge is on, and then the O group will attack on the opposite face. And that's what I've drawn here. So we went from this structure to this structure and this structure to this structure. And these two are enantiomers. These two are also enantiomers. The final step is just a simple deprotonation, which I've shown in a different mechanism we just went over, where we're just getting rid of this extra H group because we don't want to have an overly filled oxygen. The oxygen just likes to have two bonds, so it's just going to remain attached to this H group rather than two H's. So we're going to deprotonate that with the excess water molecules that will always be in solution and form our final answer, which is going to look like this. And once again, like I said, it's an anti-addition, and you can check that by looking here and seeing that this bromine is on a different face than this OH, and in this case, it's also on a different face than this OH. So that is my review of the 4 reactions. I hope I didn't go through it too fast. Please let me know if you have any questions, text on the group. And overall, the mechanisms are not too difficult. As you can see, they're not multi-step, but these are the foundational mechanisms or mechanistic characteristics that you'll see used over and over again in the more complicated reactions you'll learn in Orgo 1 and 2. So these 4 reactions, I would honestly say, are some of the most important ones you'll learn in Orgo 1, because learning how to deal with carbocations, learning how to deal with bridge species, learning how to deal with the stereochemistry, which can get quite complicated, as we saw in this case, that will all be very helpful when you get to harder and harder mechanisms. The last thing I wanted to mention is that when you make your reaction guide, as I've done here, I've copy and pasted sections from my own reaction guide onto this review. When you make this, include a section if you want about what the purpose of the reaction is. Because when you get to the end of the semester or the end of this section and you're asked to do synthesis reactions, you're basically synthesizing a molecule with an intention. You're either trying to put an OH group on it, you're either trying to put a bromine group on it. So categorizing these with that intention can help you organize them in your mind. So that's what I've done here. This hydrohalogenation reaction, the purpose and the intent of this reaction is to add 1 mole of an H, or 1 mole of an X, which X represents a halogen, either bromine, chlorine, or iodine. Acid catalyzed hydration, you're adding either an OH group or an OR group. Adding bromine and chlorine, you're adding 2 moles of a halogen. And adding HOX or halohydrins, you're adding either OH or OR plus an X. So those are the purposes of all 4 of these reactions. They're pretty straightforward reactions, but let me know if you have any questions, and good luck studying for this next exam.